Before I start, I just read a message that says people cannot see my video. Is that actually correct? Okay. All right. So it sounds like a few people cannot see me, but mostly it's just Ander. Okay. Hi, Ander. Hello, everyone. I think it's I'm extremely honored to be here. It's a really terrific initiative by Life and Andreas.
Ah, tienes razón. ¿Sabes lo que puede haber sido? Que lo dibujó la misma persona.
Okay, I muted him. I can also not see you actually.
Ah, okay. So a few people cannot see me.
Can anybody see Nathanael? Oh, many people can see you. Okay, good.
Right.
Okay. 200 people said yes.
Yes, I can see.
Go ahead.
So, okay, it's not clear why some people can see me, but why some people cannot. So I think the important bit is that you can listen to me. Not sure how to ask the question, whether you can hear me. Life, do you want to ask if there are some people who can not hear me?
Anybody cannot hear Nathanael?
Just need to resize the screen. I don't know how to resize.
Good idea. Oh, wonderful. Perfect. Yeah, just resize the screen.
Resize the screen. Do I have to?
I think now everybody can see you.
Okay. Giovanni says that he cannot not hear me. Okay. I think that's a pretty good sign. I don't have to do anything. Excellent. So I'm extraordinarily pleased to be here. It really is an honor, and I think this initiative by Life and Andreas is absolutely terrific. I'm so happy that they thought of organizing something like that. It's going to be, I think, a great tool for all of our community not only in the months ahead, but I hope in many years in the future. So I want to tell you a little bit about some very recent work. In fact, it was posted on the archive just a couple of days ago. This is joint work with Yuan Guine from the University of Cambridge. And this is going to be about random walks on random planar maps and something called Liouville Brownian motion. The first thing to begin with, what I'm going to do is I'm going to give you a bit of motivation. It starts with a wonderful and remarkable paper of Itai Benjamini and Note Tram from 2001, where they asked basically the following question: what does a random walk on a random planar map look like? And the kind of planar maps that they had in mind are the ones that you can see on this slide here. This is something called, well, it's something related to the UIPTs. This is the kind of random planar maps they had in mind, introduced by Omer Angel and Note Tram roughly around the same time. And it's not going to really matter for the rest of the talk, but for those of you who know about this model, it's called the UIPT. It's a very beautiful model of a random planar map. What this is really just the local limit of random triangulations with n faces as n tends to infinity. So we should imagine the limit of this picture that we see on the slide when the number of faces n tends to infinity. And the reason why they
Nathanael, sorry to interrupt. People cannot see the entire slide, probably because all the options of Zoom take away the bottom. So perhaps it's better if you don't go for full screen mode.
Let's try this way. Is that better?
No, it's still too big, at least for me. Better?
Is that better for everyone? Is that better for you, Live?
No, it's not really. So it's still a bit too big.
Where does it cut at the moment?
Ambient. So the first row is there.
I see. It's just one line is missing, and maybe the best is it does go a little bit it is looking a bit full on the slide, but
oh, okay. It seems to be different for different people.
Okay. We are learning about this technology, obviously.
Yes.
So note for future speakers, try to not make your slides too full.
Julien says unzoom. Can you unzoom?
Can I unzoom?
Yes.
Yeah.
With a minus in your at the top of your window. Yeah.
This way, I'm sure most people will be able to see it now, I hope.
So now it's better. Yeah.
Okay. So the reason why Benjamin Ishram considered this kind of question had to do with non-rigorous works from mathematical physics, basically work of Ambion and Watabiki, roughly around the same time, non-rigorous of course, in which they claim that, so let me put it in quotation mark, the spectral dimension of Liouville quantum gravity should be 2, meaning basically that if you're considering, if you're working, if you're looking at random walk on this kind of graphs and you're asking what is the chance that your random walk is back to its starting point after time t, then as t tends to infinity, it should decay in the same way as it would in 2 dimension, meaning it would decay roughly as 1 over t. And you know, 1 over t is of course something that you know, if you sum it, you get infinity. And so it led them to conjecture that UIPT, this limit of random triangulation with n faces as n tends to infinity, should be a recurrent graph almost surely. And they couldn't quite prove that, but they proved something very related to that. They proved the following fundamental theorem, which really spurred a lot of work following this paper, and initiated a very successful program of research. And the result of the theorem says that subject to bounded degree, any local limit of a sequence of planar maps rooted at a randomly chosen vertex is going to be recurrent. So the UIPT does not have the property that is bounded degree, but it's very close to that. In fact, there is an exponential tail on the degree of randomly chosen, uniformly chosen vertex, the root. And so this strongly suggested that this conjecture was correct. And in fact, this problem was famously solved in a paper of Gorel Gorevich and Asaf Nachmias in 2013, where they showed that indeed an exponential tail on the root, on the degree of the root suffices, and in particular, the UIPT is recurrent. So for this is not going to be, the core of what I'm going to talk about in this talk, but it is, nice to have in the back of your mind, perhaps. And for people who are interested, I would strongly recommend taking a look at Asaf Nachmias' Saint-Flour lecture notes for a recent survey. So this talk won't really be about these results. It will be about a related question. Really, it will be about scaling limits of random walks on such graphs, on such planar maps. There's 2 things I want to do in this talk. The first thing is to tell you about what is the candidate for the scaling limit. This is going to be the Liouville Brownian motion from the title of my talk. And then I want to tell you about a result where we prove some scaling limit result for random walk on a class of planar maps. And this class of planar maps will be maybe intuitively related to the UIPT, but will not actually include the UIPT, and that's why you don't really need to know what is the UIPT for this talk. I will describe these maps in more detail later on. Okay, so my first task is going to tell you a little bit about the candidate for the scaling limit. And to do that, I need to tell you a little bit about something called the DDK Ansatz, which is something that came in the physics literature. And really, it was explained to the probability community in a landmark paper by Bertrand Duplantier and Scott Sheffield, roughly 10 years ago. And this ansatz roughly says the following. It says that the metric, these random walks, these random planar maps should be related to a random geometry in the plane, where the metric should be taking the following form. it's so this is a bit of the metric, and it should be proportional to the exponential of gamma, where gamma is a parameter, times h, where h is a Gaussian free field. I will come back to that in a second, multiplied by the standard Euclidean metric. And maybe the best way to think about what that means, what that might mean intuitively, is that if you take a small disk of area epsilon measured according to the Euclidean metric, then really this should correspond to a number of triangles on your planar map proportional to e to the gamma h times epsilon locally at a point. So maybe this is still a bit vague for the moment. I will go in a bit more detail in a second. So first of all, what is the Gaussian free field? Maybe many of you are familiar with it, but maybe some of you are not. You should think of the Gaussian free field as a random function going from some given domain D into the complex plane. It's a very canonical object. I put function in quotation mark because actually it's not defined pointwise. Rather, it's a random distribution, meaning that what's well defined is local averages of the Gaussian free field. So what does make sense is to integrate h against the test function f, and then by definition, what you get is a Gaussian random variable with mean 0 and variance sigma squared, where the sigma squared is given by this formula, the double integral of the green function gxy times f of x, f of y, dx, dy. And g, as I said, is the green function in the domain D. So this formula, the way you should think of it is that it says that basically, well, the Gaussian free field is not a function, but if it were a function, then its pointwise values would be Gaussian random variables with mean 0 and a covariance given by the green function gxy. And as many of you know, in 2 dimensions, the green function explodes on the diagonal. So when y converges to x, then gxy blows up logarithmically, in fact. And that's another way of saying that the pointwise variance is infinite, meaning that you cannot assign values to this function pointwise. But again, what really makes sense is to integrate h against the test function f. So you get a random distribution. So, this formula, this is an ansatz from physics, and it's not so clear how we can really make sense of it. Really, the core difficulty, if you want, is that h, as I just said, is not pointwise defined, but rather is a distribution. So you cannot easily exponentiate a distribution because it's not clear, what that means. So one way to think about this problem is that h is well defined when you integrate it against test function, and that really is because there are, when you do this integration, when you take a local averages of the field on some given region, you can think that there are lots of plus and minus infinities that cancel each other, but when you take the exponential, then there's no reason for this cancellation to take place anymore. And so it's not clear at all what exponential of the Gaussian free field can mean at all. Mathematically, the problem, if you want, is the following. We know what is the Gaussian free field H, but it's not so clear what exponential of the Gaussian free field might mean. And there are really 3 types of objects that one might want to make sense of. The first one, as I said, is the metric, really. Can you measure curves in a way that the length of curves in a way that depends on this Gaussian free field, and you want to sort of integrate exponential of gamma times the Gaussian free field along a curve. In reality, it's a bit more complicated than that, but let's not get into this complication for now. Likewise, another object that you might want to make sense of is the volume measure. So that would be integrating exponential of gamma times the Gaussian free field times dz on some given set. So that's a way of assigning random areas to sets in the plane. And finally, the third object that one might care about is a diffusion, so a Brownian motion on this surface. And as you can imagine, for me, for this talk, I will try to insist more on the diffusion aspect of things because I care about this Liouville Brownian motion. That's one of the goals of this talk, to tell you about it. but I will tell you a little bit about some of the other objects. So the situation today is extremely fortunate because in fact all these three objects have been made sense of. The first one to be constructed and the easiest to explain is the volume measure. I will tell you a little bit about it in the next few slides. The diffusion was the next thing that was constructed, and very recently the metric associated to the exponential of the Gaussian free field was constructed. This is a series of 6 papers that appeared all on the same day on the archive. That was really quite amazing. 5 of which written by Ewan Gwine and Jason Miller, and a 6th one written by Julien Dubeda, Hugo Falconet, Ewan Gwine, Josh Prefer, and Shinsa. And this construction of the metric generalized an earlier result, which was really a breakthrough by Jason Miller and Scott Sheffield, which constructed the matrix for the special value of the parameter gamma equals square root of 8/3, which actually plays a very special role in the theory. So I will tell you, I will start by telling you a little bit about the volume measure, because it's the easiest object to construct and to explain how this works. And that will give you, I hope, a flavor of what is this random geometry. So, well, the idea is maybe quite simple in principle. We cannot assign pointwise values to the Gaussian free field. So instead, what we can do is we can regularize the Gaussian free field. So we're going to consider h epsilon of z. So that's going to be some regularization of the free field for convenience. Often people choose it to be the circle average of the free field. So you just consider the average value of the field at a distance epsilon from a point z. And this turned out to be actually well defined. But you know, this is just one choice of renormalization and actually of regularization, and actually you could think of different choices. And the theorem, which was proved in various forms by various authors, but maybe it's important to mention the work of Kahan in 1985, because really this goes back to his theory of Gaussian multiplicative chaos. And then this was rediscovered by Duplantier-Sheffield in their landmark investigation, explaining how to think of Liouville quantum gravity from a probabilistic point of view. And then further discussed in works by Shamoff and myself around 2017. Then the idea was to say, well, so what we're going to do is consider this epsilon regularization of the Gaussian free field, exponentiate that, and view that as a random measure. We can integrate that, and we can then try to let epsilon tend to 0. And of course, if you do that, then you will have to renormalize things appropriately, and that turns out to be the right renormalization. And so this limit that you get is a measure, it's a random measure, which is called the Gaussian multiplicative chaos associated to the Gaussian free field. And rather than trying to explain things about it, a picture is worth 100 words easily, and there's going to be 3 pictures, so you can imagine how many words I'm putting in there. So here's a nice visualization of Liouville measure. This is a simulation due to Rémi Rode. And what this shows is an approximation of the density of this Liouville measure with respect to the Lebesgue measure. I mean, of course, this density is actually infinite in reality. So this is a density of the measure for a small epsilon, for which actually this density exists and is finite. So you see a picture of this approximate density, if you like. And here we've got a value gamma equals 0.2. And as you can guess, then you get some object that's very spiky. Even though when gamma is very small, we should expect to have a measure that's actually very close to the Lebesgue measure. Now, when I increase the value of gamma, the peaks, they become more and more pronounced. And I get an object that looks more and more degenerate. And it turns out that there is a critical value of the parameter gamma, which is gamma is equal to 2. And beyond this value, the measure actually degenerates, and you get something that is 0. But for smaller values of gamma, the measure exists and is non-trivial. And so here, this is a simulation of this density for gamma equals 1.8, so very close to the critical value. Okay, so my next task is to tell you about Liouville Brownian motion, and because that's one of the main topics of this talk. And if you want, the question again is, how would you define a canonical Brownian motion in this random geometry? And if we were dealing with Riemannian geometry, there is a standard procedure to do that. Really, the metric defined what's called a smooth connection, so a way of differentiating function if you want. And that induces a Laplace operator, delta, and Brownian motion on the manifold is then defined in terms of this Laplacian. That's the generator, the infinitesimal generator of the process. And of course, in this context, in this random geometry, we can sort of forget about this approach because it seems a bit hopeless to try and differentiate things. So I think you have to invent something else. And so this was something that was done in 2 simultaneous papers. The papers have appeared at different dates because of different procedures in different journals. But there was one paper by myself and another one by Christophe Garban, Rémi Rode, and Vincent Vargas. And the idea was to do regularization procedure again. I'm using here their formulation, the formulation in the paper by Garban, Rode, and Vargas, which is maybe slightly easier to explain at first. And anyway, their paper goes much deeper than mine. So the idea was, if you want to define the appropriate diffusion in this geometry, then informally or formally, maybe I should say, then we would want to consider an isotropic process. So the dz, the value of the process, the way it changes in a small increments of time, should be proportional to the way a Brownian motion moves. But the amplitude of this Brownian motion is changed according to a factor, which is roughly e to the minus gamma over 2, that just a way to scale things, times the Gaussian free field. And in reality, we have to do something similar to what I explained in the case of the Liouville measure. Namely, we consider first a regularization of the Gaussian free field H epsilon. And you have to scale this appropriately. This turns out to be the right factor. And maybe another way to restate what this definition is simply that I can start with a Brownian motion B in the domain of the complex plane. And I define this function phi epsilon of t, which is just the integral from 0 to t exponential of gamma times the Gaussian free field at the point B of the Brownian motion times ds. So I call this the clock of Liouville Brownian motion. And then by definition, the epsilon regularized Liouville Brownian motion is just the Brownian motion B time changed by the inverse of this clock. And the theorem that's contained in these papers, and as I said, this paper, the second paper by Garban, Rode, Vargas actually goes much deeper than that, says that the limit exists on compacts of time in probability, say, as epsilon tends to 0. So this gives you an idea of how you would want to define Liouville Brownian motion. And at this point, I have something that I want to share, which is a video of Liouville Brownian motion. Now, we have tried to share video earlier, and actually we run into problems when we did some trials with Leif and Andreas earlier. And so instead, what I will do is I will send you a link on the group chat, if I manage to find it. Do I manage to find it? So I have to stop sharing my screen for a second, and I will share I will share the link to the video. So I have just sent to everyone. No, not to everyone. How do I send it to everyone? I do not know how to send it to everyone. Put it here. Yeah, well, I'm trying to put it here, but somehow I can. There we are. No. Drop down menu. This is annoying. I can I can only send a private chat for some reason to Christophe Garvan.
Send it to Christophe, and perhaps Christophe can send to all.
So maybe Christophe, if you know how to send it, you can send it to everyone. Send it to me into field. Yeah, I don't know why.
Oh yeah, because it's there.
To everyone. There we are. Thank you, Christophe. And here is the link again. So you can send to everyone. You can go to this. This is a YouTube video which was made by Henry Jackson some years ago. Henry Jackson is a former PhD student of mine, and he made this, I think, beautiful simulation of Liouville Brownian motion. I will play it for myself as well, even though I have looked at it many times. What you see on this video is a couple of different things. First of all, you see a green mountainous landscape. That's the value of the Gaussian free field. And you see also on top of that, a particle moving on this mountainous landscape. So I see some people saying that you can only see my face, and that's because in order to see the video, you have to go to YouTube and follow the links that I've finally managed to send on the group chat. So this is an amazing video. I will give everyone the chance to see it again. Yeah, so maybe a couple of comments. As you can see, this particle likes to spend time on top of mountains, and the reason why that's the case is not because it's attracted somehow to the top of the mountains, but rather because when it finds itself on top of a mountain, it is slowing down so much that it looks like it's you know, it's hanging out there. So I hope everyone has seen the video and try to got a feel for what this process is doing. For now, I will return to my slides, and I will tell you a little bit.
There's one question. We could try a question.
There is a question. Sorry, I didn't see this.
So if you raise your hand, you're going to the top, and we're going to unmute you. Let's see. Raising hands doesn't work. Perhaps you can read the question yourself in the chat.
Yes. So.
Oh.
Actually, it's not easy for me to read the questions in the chat for some reason. Maybe I can.
Okay, let's.
The question is in simulation. It keeps moving because people keep writing things. In simulation mounting can go deep under the plane. Can random walk go there? In the simulation mounting, can the random walk go into the deep crevices?
Yes, that's right. So there's really two things that's happening. So really the trajectory itself, maybe I explained this too quickly, maybe you can still see it in the slides. The trajectory itself is just a time change of Brownian motion. It has no preferred direction. It is completely isotropic. But what is happening is that it can move more or less quick depending on the values of the free field. So that's exactly the meaning of this clock. The clock phi epsilon of t makes it move more or less quick depending on how high the field is. So when the field is very high, then the Liouville Brownian motion is actually slowing down and spending a lot of time. And really, if you think about it, it's because you sort of have packed a lot of triangle into a small area. And so that's why really, Liouville Brownian motion will spend a lot of time there before it moves elsewhere. Conversely, it can also find itself in places where the field is just very low. And in those places, the Brownian motion will actually move extremely quickly. So it will see these points if you want, but just spend very little time there. And so thanks. These questions are very useful. I see that somebody asking a question: are the peaks supposed to denote local maxima? So maybe I should explain again what this was. This was a regularization of the Gaussian free field, because we cannot give pointwise values to the field. And so, of course, the absolute top peak will be local maxima, but only of this regularization. So in reality, yeah. So in fact, this is a good way to come back to my slides and tell you a little bit more properties of this Liouville Brownian motion. So there are various properties that we know, many of which were proved in the paper that I mentioned by Christophe Garban, Rémi Rode, and Vincent Vargas, or another follow-up paper that they had after, and also another paper by Rémi and Vincent, Rémi Rode and Vincent Vargas, one paper by myself, and another paper by this PhD student, former PhD student of mine that I've mentioned, Henry Jackson. One property that we know, for instance, is that this process has continuous trajectories and does not stay stuck. So this might seem obvious, but actually, if you think about it, the mountains might be so high that the Brownian motion wants to kind of stay stuck there and does not want to leave the peak. And in some sense, that is actually what happens when gamma becomes greater than 2. The mountains are so high that just Brownian motion never leaves these positions. I see that somebody raised their hand. I don't know if it's possible to make them unmute themselves.
Yeah, I'm not seeing the raised hand.
Okay. So maybe group chat is easier for people to ask questions if they want to.
I would hold the questions till the end, just for the sake of context.
Okay, all right. So just because maybe there's too many people, maybe questions are best left till the end. So another property that we know is that Liouville measure, the measure I introduced a few slides ago, is actually almost surely invariant for Liouville Brownian motion given the free field. So this is an indication, if you want, that we are really looking at the right object. Another property that we know is that it actually spends, this process spends all its time in a set of Lebesgue measure 0. So that's quite weird. By all its time, I should say that, Lebesgue all of its time, almost all of its time in a set of Lebesgue measure 0. And that's because it spends most of its time in places where the free field is going to be unusually high. And so that's one reason why that's the case. Another weird property of Liouville Brownian motion, at least weird to me, is that when gamma becomes a bit greater than square root 2, so this is still less than the critical value for which things make sense. I remind you that the critical value for things to make sense is gamma equals 2. So gamma can be greater than square root 2. For gamma greater than square root 2, the trajectory actually has 0 derivative at almost every time. And that's related again to the same phenomenon that it likes to spend time at these places where the free field is very high. So there are mountains that are quite high, and these really slow down a lot the process. Not quite enough that the process would stay stuck, but enough that there is 0 derivative at almost every time. Finally, another remarkable property of this process is that the spectral dimension was rigorously computed by this paper of Rémi Rode and Vincent Vargas, and they confirmed this conjecture of Ambjorn and Watabiki that the spectral dimension really is 2 almost surely, meaning that if you look at the on-diagonal transition probability of Liouville Brownian motion, then PTXX behaves to the first order that is up to logarithmic terms like 1/t. as t tends to infinity. Right, so this was a very brief introduction to Liouville Brownian motion, which is a candidate for the scaling limits of random walks on planar maps. I want to start telling you a bit about the results that we proved. And for this, the first thing that I need to do is to try to tell you about potential connections between discrete side of the story and the continuum side of the story. And by discrete, I mean random planar maps. And by continuum, I mean Gaussian free field. So, physicists, because of this DDK Ansatz that I've mentioned at the beginning, which was explained to us by Duplantier and Sheffield, really, it is largely believed that these two stories should be two sides of the same coin. And if you want to try and say this rigorously, then the first thing you need to do is you need to find a good way to draw your planar maps in Euclidean space. And the reason this is necessary is because the planar map really is a combinatorial object. So I never gave a definition of planar maps, and maybe I should. A planar map is really just, is very similar to the notion of planar graph. The planar graph is a graph that you can draw on the plane in such a way that the edges don't cross one another. And a planar map is very similar. It's basically the idea of a planar graph that you have drawn in the plane in some particular way that you considered up to a homeomorphism of the plane or on the sphere if you're doing this on the sphere, which may be more natural, depending on the context. So the fact that we consider it drawn into the plane but up to homeomorphism just means really that we are still considering a combinatorial object. It is not a particular drawing that we consider. It's a drawing up to homeomorphism, meaning that I can draw my map in the plane in a way, and I can move the edges in some arbitrary way, and for me that will still be the same planar map. So finding a canonical way of drawing planar maps in a plane is actually an important question if you want to try to relate the discrete and the continuum stories, because the continuum stories, they make reference to specific positions of points in the plane. There are many ways you can do that. There is the Riemann mapping theorem provides a way, the uniformization, I should say, something that is very popular and leads to very beautiful pictures, one of which was shown as the first slide of my talk, is a circle packing theorem. This picture, by the way, was due to Jason Miller, who has many amazing pictures on his webpage. So the circle packing theorem provides one way. I want to talk a little bit about Tutte embedding because it's going to be more relevant to the rest of my talk. And the Tutte embedding, whether you speak, well, I should say that this Tutte embedding comes in two flavors. There's either the flavor for infinite maps or the flavor for finite maps with a boundary. So I will talk briefly about the Tutte embedding for finite maps with a boundary. And so this is what you see on this picture, also due to Jason Miller. And what you can see here is a large random triangulation with a big boundary. So the boundary vertices have been drawn here. And so a Tutte embedding of this triangulation is just a drawing of the graph in such a way that if you do a random walk on this graph, then the position of the random walk will by definition be martingale. So another way to put it, of course, is that the position of any vertex must be equal to the average value of the positions of its neighboring vertices. So it's not very complicated to see that you can do that, simply because once you've prescribed positions for the boundary vertices, you can simply solve the discrete Dirichlet problem with this boundary data. And the solution of the Dirichlet problem will tell you where to put the vertices. And if you do that, then of course, by definition, then every vertices will be the average of its neighbors. Now, the remarkable thing, which is a theorem of Tutte, is that actually, if you do that and also draw edges as straight line, you will get a planar realization of your planar graph. And so that means that straight segments drawn in this fashion will have the property that they don't cross one another. They might be tangent to one another, but they will not cross one another. So that's a beautiful theorem of Tutte. And so you know, the fact that random walk on this graph is by definition a martingale, of course, is a very nice property. It says that it's a canonical way of drawing the graph on the plane. Okay, I see that on the group chats, there are still many people asking questions about Liouville Brownian motion and high point of the Gaussian free field. So maybe these questions can be deferred to the end. I'll be more than happy to take
Nat, I think they've started discussing among themselves and answering each other's questions.
Yes, your friends answered most of the questions.
Yes.
Okay. Great. Okay, thank you.
We don't need you.
Okay, excellent. So that's the Tutte embedding. Once we've got a good way of drawing graphs in a plane, it makes sense to ask questions about relating the discrete and the continuum stories. And here's a big conjecture, which I think at this stage today is still quite far open, quite wide open. And so here's what it says. So let's take Tn some uniform random triangulation, say with n faces, or say with a boundary as I did just above. Let psi be some nice embedding of this triangulation into the plane. For instance, it could be circle packing, or it could be the Tutte embedding that I discussed. Let mu(n) be the mass measure, putting mass 1/n at each center. Okay, I really should have said at each vertex of the graph. And one conjecture that you can make is that as n tends to infinity, this measure converges at least to a variant of Liouville measure for the specific value of the parameter gamma, which is square root 8/3. I've already mentioned actually that this value plays a special role in the theory. And moreover, if you were to do a simple random walk on your graph embedded in this nice way, then the image of the random walk under this embedding would converge after scaling of space and time towards Liouville Brownian motion. And so I've finally got to a stage where I could at least tell you what was the question we were trying to approach with you and Gwyn in this paper that I want to tell you about. Right. So here's the main result. At least I will tell you the punchline of the result, and later I will try to say more precise version of this punchline. Maybe Life, you should also tell me how much time I've got at this stage, because I didn't really pay attention to the
Since you're the second speaker, there's no problem, I guess.
Oh. So I can speak for 1 hour, right?
Yeah, just
no, I won't speak for 1 more hour.
10 minutes or so.
10 minutes, yeah, right. So I will try to do that. Thank you. So the punchline of this paper that we put on the archive just a couple of days with you and Gwyn is that we proved the first such result for a class of planar maps called Mated-CRT planar maps. By this, I mean we proved the first result where we show that random walk embedded, random walks on this graph embedded in a nice way, meaning basically Tutte embedding converges to Liouville Brownian motion. I will tell you about these Mated-CRT planar maps. They are really remarkable planar maps. There are sort of 2 ways you can think about them, and these 2 ways are very different from one another, and they tell you 2 very different things. The first one, the first way you can think about this Mated-CRT planar maps is as a very nice discretization of Liouville quantum gravity. So maybe you can think that these are planar maps that are devised so that they are close to Liouville quantum gravity. And of course, so they are, the first candidates you should try in order to try and prove any limiting result of the kind that I've mentioned. So that's the first approach. And the second approach looks very different on the surface. And I will not say much about it because it takes time. But what is very nice about this second approach is that it gives you a way of trying to relate more natural models of random planar maps to these Mated-CRT planar maps. So you can view them and sometimes rigorously view them as coarse-grained versions of more natural objects, such as UIPT. So here's a bit more about these Mated-CRT maps. Again, maybe I've hinted at this already when I said it depended a little bit in terms of embedding, whether we considered finite maps with a boundary or infinite maps with no boundary. And again, these Mated-CRT maps, they come with at least 2 flavors. In fact, more than that. I will restrict myself to these 2 flavors. One is the finite type of planar maps with a boundary. And so these corresponds to maps with the topology of a disk, basically, a simply connected domain with a boundary. Or they can be infinite without a boundary, meaning that they correspond to the topology of the sphere, or if you want, the whole plane, the compactified plane. So for each of these 2 cases, there will be, as I've hinted at, 2 descriptions, 2 equivalent descriptions. One which is directly related to Liouville quantum gravity, where you can really see that it's a nice discretization of Liouville quantum gravity. And another one which is really very different, feels completely different, which is a topological gluing of a pair of continuous random trees. This second description takes more time to explain, and I won't try to do that because it will take too much time. But they are 2 very different approaches. The fact that these 2 approaches are the same, are equivalent, is due to very deep work of Duplantier, Miller, and Sheffield called the mating of tree approach to Liouville quantum gravity. So I will tell you a little bit about just this description 1, the first way to describe this Mated-CRT planar maps. As I said, so this is maybe easy to describe, especially if you're a bit familiar with SLE and Gaussian free field or Liouville quantum gravity. So we're going to start with fixing a parameter gamma between 0 and 2. Maybe at this point I should emphasize that I've sort of advertised a bit more the case gamma equals square root of 8 thirds, but actually the result I'm about to state is valid for any gamma between 0 and 2. That's the whole range of values for which we expect these things to make sense nicely at this point. And we're going to start with H being something called a quantum cone. Now, a quantum cone takes a bit of work to define very carefully. So I don't want to do that very carefully, but a good way to approximate a quantum cone or to have a picture of what is a quantum cone is basically a Gaussian free field in the full plane to which you've added a term of the form gamma times log 1 over z, where gamma is your parameter between 0 and 2, and z is just the point in the complex plate at which you evaluate your distribution. So H is not exactly, I should say, really this formula, but close enough. And it's called the quantum cone. It's basically just a Gaussian free field plus gamma times the logarithmic singularity at the origin. And we also consider eta an independent space-filling SLE curve with parameter kappa given by kappa equals 16 over gamma squared. Now, because gamma is between 0 and 2, gamma squared is between 0 and 4, and so 16 over gamma squared is between 4 and infinity. And if you're a little familiar with SLE, you will know that for kappa greater than 4, SLE is a curve which touches itself, and in fact, for kappa greater than 8 is actually space-filling. So here, what we consider is the space-filling version of SLE kappa, whatever the value of kappa between 4 and infinity. So when kappa is actually greater than 8, this corresponds to gamma being smaller than square root 2, then actually space filling SLE kappa is just ordinary SLE kappa. But when kappa is between 4 and 8, then the definition of SLE needs to be modified a little bit in order to get the space filling SLE. Actually, it's not trivial to come up with a definition of space filling SLE, but it has been done in some earlier work of Jason Miller and Scott Sheffield on imaginary geometry. So at any rate, we've got this curve. It's possible to define it, and it is space filling. It's independent of this quantum cone, the Gaussian free field plus a logarithmic similarity at the origin. And the way we're going to get a graph, G epsilon, with these two data is the following thing. We're going to break the plane into cells. Right, so this is not the right way to describe it. I apologize for that. I'm going to break it into cells. Maybe you can see it on this picture a little bit, into cells in such a way that each cell has a mass mu h in terms of mu h of size epsilon. So I run my space filling SLE curve, and I wait until I've covered epsilon amount of mass, where the mass is measured according to the exponential of the Gaussian free field. And that gives me one cell of the graph. And then I keep going, and I run the SLE curve a bit more until I've covered epsilon amount of mass again. And that gives me a new cell for this. So if I run it in the full plane, so here the picture is written in the disk, but actually you should imagine this picture in the full plane. When you do this construction in the full plane, then what you have done is you have broken up the entire plane into regions, each of which measure epsilon in terms of the exponential of the Gaussian free field. So, so this is a way of breaking up the plane into cells. And to get a graph out of that, I will just simply put a vertex at the center of each cell and declare vertices to be adjacent if the cells are adjacent. So that's the way these Mated-CRT maps can be defined. At least that's one description of these Mated-CRT maps. Maybe it's already clear from the way I've described them that they are made to be a nice discretization of Liouville quantum gravity. There is a second description of this Mated-CRT maps. I don't want to say much about it, but just to give you a flavor of what it is, you will see that it looks totally different from what I've just said. We can consider a pair of correlated two-sided Brownian motions, L and R, whose covariance or whose correlation coefficient is given by minus the cosine of 4 pi over gamma squared. And these two Brownian motions can be used to define continuous random trees, and these continuous random trees can be glued topologically in some appropriate way. And that turns out it's really not obvious to see, but it's a deep fact to do with this paper of Duplantier, and Sheffield, that this actually describes the same object. And the reason why these maps are interesting is because there are these bijections relating many models of planar maps to something close to this second description. So I will just state my result, and then we'll stop here, I think, because it will be time. And the statement of the result, when I've done it, I start with this graph G epsilon that I've described above, this Mated-CRT maps, starting from a point Z in the complex plane. And I linearly interpolate. I rescale it in such a way that it will take off, basically it will take off order 1 to leave a macroscopic region for this random walk once it's embedded appropriately. So I look at the time it takes for the random walk to leave a ball of radius a half. That's just what we take. And once it's been embedded appropriately, and we just rescale time by this factor. And the theorem that I wanted everyone to see, and which is you can find on the archive in this paper with Yuan Guan, says that for any z, if I look at the conditional law of the embedding of the walk, speed up by this time scale, then this will converges in probability towards the rescaled law of Liouville Brownian motion with parameter gamma starting from z associated with this quantum cone. Actually, this is also true in this case if we are considering the Tutte embedding. Okay, so I think I'm basically running out of time. So rather than going into a rough sketch of the argument, which will take way too much time, then I will simply stop here and thank you for your attention.
Thank you very much. So unfortunately, many of the questions were answered by your friends, but I guess there might be still questions left. And I think one question was not completely answered. So we try, as we said in the beginning, have a look at this button, raise your hand, in this participation window. And I'm going to unmute you. Or alternatively, I could also mute everybody, and we hope that not 10 people are going to ask at the same time. What do you think?
Ooh, dangerous.
Okay.
Now
everybody. If somebody wants to ask a question, just go for it.
That's why I sent it to you.
Uh-huh.
I think that we've not been really good.
Si vous étiez là à regarder les chats, les gars, tout ça.
It doesn't work. Too noisy, yeah. This doesn't work. So my impression was that many questions have already been answered. So, oh yeah, there's a hand. Okay, yeah, you should be able to ask.
Okay, let me try that. Maybe it's just a very simple question. But for one-dimensional diffusions, you have this concept of a speed measure, and which tells you basically, like if you have a one-dimensional martingale, you only have to say how fast it exits a certain interval, and if you know that for every interval that is what the speed measure tells you, then you basically know which one you have. And I wondered if for isotropic diffusions in the plane, you could do something similar. If this is basically what is happening here with this special measure mu-h.
I think that's right. Yeah. Yeah, I think that's basically right. Right. That's just. I mean, basically what it is a form of Dubin-Schwarz theorem, right? It's isotropic and moves at equal speed in all directions. So Dubin-Schwarz just tells you that you should be able to express your diffusion in a situation like that as a time change of Brownian motion, where the time change involves just a quadratic variation. And if you want, you can think that the Liouville clock that I mentioned in my talk just defines the quadratic variation of your process effectively. So basically that's right. So if you've got something that is isotropic in the sense that I've just described, right, that it has no preferred direction, it's a martingale, and the quadratic variation in every direction is the same. And of course, so you need really, isotropy really means also that the cross variation will be zero. Then by definition, you get exactly that. You get, I think that's called the Knight theorem, which is really just a generalization of the Dubin-Schwarz. So basically, that's right.
Okay, thanks.
Okay, next one is Milton. So I changed the option, so now everybody can unmute him or herself. The next one is Milton.
Okay, so when people look at the diffusion in fractals, actually what they do is that they try to define this Carré-Duchamp measure.
Mm-hmm.
And once you have this measure, you can just use the theory of discrete forms to define Brownian motion of this object. Is there a strategy here that analogous to that somehow?
Right. So I should say that I'm really not the expert for this. I believe Christophe, Rémi, or Vincent would be much better at answering this question than me. They have in their paper they do discuss the Dirichlet-Form approach to Liouville Brownian motion. I think in practice here it would be very hard to directly relate the Dirichlet-Form. So in fact, our approach does not use this directly. I don't know if I've answered your question, Milton.
That's okay.
There's another question in the chat, but I fear it's already answered again by your friends. Can you see it?
Oh, right. Do you use bijection machinery in your proofs? So not really, no. So I mean the proof that we have is based on sort of two things. I mean, you know, it's a sort of tightness plus characterization type of argument. I think, you know, several aspects of these proofs are it's quite modular, and I hope it's quite generic. So you know, we're hoping that some aspects of this proof will be useful when we try to talk about convergence on other models of random planar maps. It does not really rely so much on bijections. It's more to do with, on the one hand, sort of energy estimates, I would say, to try and get some tightness. And on the other hand, a characterization of Liouville Brownian motion, which roughly says that there is a unique Markov process whose law is a continuous function of its starting point, is Markovian, and time change of Brownian motion, and leaves Liouville measure invariant. And that's the characterization that we use at the end of the day to prove convergence.
There are two more questions. The first seems to be answered already. The second, you're lucky.
Okay, so Leandro asked, can the gamma Liouville Brownian motion be defined on the limit in the limit for gamma equals 2 by taking, yeah, right. So Leandro, thank you. That's indeed a definition exists for gamma equals 2. That's been done in a paper by Rémi Rode and Vincent Vargas. Right, so in principle, there is also a recent mating of tree approach in the case to Liouville quantum gravity in the case gamma equals to 2. There's been two papers, one by Nina Holden and Ellen Powell, which prove a version of the mating of trees story. And I don't know to what extent it might make sense to try and prove. I've not thought about it, about the case gamma equals 2 for the scaling limits of random walk. It's a natural question, obviously.
So it looks like there are no more questions. So thank you very much again, Nathanael. Thank you very much, Andreas. It's not so easy to give a talk in just a computer camera without any people around. So thanks for being the first for trying this.